Hi, John. John?
Hi, how are you?
Good. How are you doing tonight?
Good. Sorry, I couldn't click the mute button.
Oh, that's fine. All right. So let's talk about integrals of trig functions.
Okay.
Okay. I'll try to do this quickly and without getting into too complex of a level. Can you integrate that? Think U-Substitution.
Would we set U as sine squared x?
No. U is sine x.
Sine x?
Yeah, what's du dx?
Oh, cosine x.
Aha. You see the pattern?
Yeah.
We're looking, that's 90% of your U-substitution problems are going to be a function multiplied by the derivative of its inside.
Okay.
When you see that, you can just apply the power rule to this part. So that would equal sine cubed over 3. Differentiate that. What do you get?
You will get sine squared x.
No. You got to multiply by the inside. That's the derivative of the outside only.
Sine squared x times cosine x.
Aha. That's what we were looking at. Okay?
Okay.
Me? All right.
Yeah.
So, differentiate that.
Or integrate or differentiate?
I meant integrate it, yeah.
So then U would be sine x again. So then du would be, du dx would be cosine x. Wait, we don't need U substitution for that.
Exactly. You can't do this by U substitution.
So it would just be sine cubed x over 3.
No, we just figured out that sine cubed x over 3 comes out to be sine squared x times cosine. In other words, this is not easy to do.
Right.
So there are 3 identities you must memorize to do these. First one doesn't apply here. Let me use the one that does apply. Let's go back and talk about our double angle formulas for cosine.
Okay.
3 of them. That's one of them. Another one is 2 cosine squared of x minus 1. And another one is 1 minus 2 sine squared of x. Okay? You probably wondered when you were studying trig why we have 3 identities for the double angle of cosine. We don't for the sine. The sine of 2x is just one identity.
Okay.
Well, this is the reason. Because we can solve and we can make cosine squared of x as a function of cosine of 2x. We can also do the same with the bottom one. So here, if I solve this for sine squared of x, here's what I get. And this is one you want to memorize for these problems. Now, that's very useful because instead of an impossible integral, I now have one that I can do quite easily.
Right.
Notice that that's the integral of what? How do I do this easily?
Would we need to use U-Substitution?
No? Well, at least not really. No. Split it up into two fractions.
Oh, the integral 1/2 minus the integral of negative cosine.
No, yeah, don't put two negative signs in there. If we're going to put the minus right there, then we don't put it again.
Okay, so then minus cosine 2x dx. Why does this 2 stay under the cosine 2x?
Well, because 1/2 minus that is this. Notice the 3/2 minus 2/2, the denominator does not change.
I thought we pulled the 1/2 out, though, and
No,
there's no...
we didn't. We separated it into two fractions is what we did. That's all we did. Okay, in other words, we've got this fraction, and we've got this fraction.
Okay.
You can always do that as long as your denominator is a monomial term. In other words, A plus B over C is A over C plus B over C.
Okay.
That's all we did. Okay? The thing is now we know how to integrate cosine of 2x. That's an easy one to integrate. That's sine of 2x divided by 2.
Right.
What's the integral of 1/2?
1x over 2.
Yeah. What's the integral? Let's go ahead and bring this to, I don't want to confuse you because I got two 2's in there. So let's take that out. Okay, you see what I just did?
Yeah.
What's the integral of cosine of 2x?
It would be sine of 2x over 2.
Perfect. In other words, we can integrate those really easily. What we can't integrate is those.
Right.
So whenever you have a sine squared or a cosine squared, you got to use these two identities over here to convert it to cosine double angle formula, because we can integrate cosine of a double angle.
Okay.
With me?
Yeah.
All right, good. Now that you understand all of that, let's handle combinations of stuff. So, let me give you a simple one first. What's that?
Well, we need to use U-Substitution.
Okay. After a while, after you do a bunch of these with U-Substitution, you actually don't have to go ahead and do the U. Just apply the power rule to that, because we can see that it's being multiplied by the derivative of the inside.
Right.
So
so that goes... So if we took... Oh. Okay. So then it would just be sine of x to the 7th. Sine
to the 7th of x. Make sure you state it like that, because it's not the same.
Right. Sine to the 7th of x over 7.
There's your answer.
Because the cosine, if we took the derivative of that,
exactly,
it would be sine to the 6th of x times cosine x.
In other words, you can use the power rule on things like that as long as it's being multiplied by the derivative of that inside, if you were to use U-Substitution.
Okay.
Okay? All right. So, now let's look at the problem you had, which was sine cubed of x times cosine squared of x. Now, here's the trick. And this is really actually pretty nifty. I don't know if you were taught this subject or not, but if it's going to be on your AP test, you need to know a little bit about it, I guess. What do we need to use the power rule?
An exponent?
We need that thing to be multiplied by the derivative of the inside, which is sine x. In other words, if this thing looked like this, I can pretty much just use the power rule, right?
Right, but we need a negative in there.
Correct. So it'd be cosine 3x, cosine third of x over 3. With me?
Yeah.
So our strategy here is to pull out exactly one sine. See what I did?
Yes.
Okay. Well, we know how to do that.
Right.
Well, what's sine squared of x?
Sine squared of x.
In terms of the trig identity. That's always,
Cosine.
it's 1 minus cosine 2x over 2. That's what it is.
Okay.
I still have this. With me?
Yep.
Okay. One advantage of doing this in Paint is I can scroll down. I can't scroll down here. The next step is always to distribute this.
Okay, so
Let me go back to the top here because I need this writing room here. I don't have enough room at the bottom. We know that what is at the top is what I've written at the bottom.
right.
It's just that I've pulled one sign, exactly one sign out, not two, one. Because that allows me to use the power rule for the rest of it. Okay, so if I distribute that, I have hold on a second. Sorry. I got this wrong. I should have been following my directions here.
Okay.
Let me start again. I'm going to write smaller this time. So that is equal to sine squared of x times sine of x times cosine squared of x. In other words, I still do exactly the same thing.
Right.
But now, instead of sine squared of x, I'm going to substitute its trig identity, which is what? If sine squared of x plus cosine squared of x equals 1, then what is sine squared of x equal to?
1 minus cosine squared of x.
Now watch what happens. Now I am going to distribute it. So I'm going to end up with cosine squared of x minus cosine to the fourth of x all times sine of x dx. In other words, is all I did was I multiplied that by 1 to get this, and I multiplied that by that to get that. And I still have my sine of x. Okay?
Okay.
Now I can distribute the sine of x, so this whole thing turns into sine of x cosine squared of x minus the integral of sine of x cosine to the fourth of x.
Okay.
And that's how you do these. Is now I can use the power rule. So what's the one on the left equal to?
The one on the left is equal to cosine to the third of x over 3.
The one on the right?
Cosine to the fifth of x over 5. And then they both have to be negative, though.
Correct.
So plus.
So, let's see if that answer is on there.
And it is.
It is?
Yeah.
Okay. Let's see, I guess I can erase that. Let's have a look at it. Yeah, number B.
Yep.
Okay.
Well, that makes sense now.
Well, and it'll handle any combination. In other words, it doesn't matter what you have as long as you have an integral. Hold on. As long as I have integral of sine to the m cosine to the n, I can do all of those problems in that manner. If m is odd, I'm going to take exactly one sine out. If m is even and cosine is odd, you still there? Yeah, hi, John. Did your computer just like reboot all of a sudden on you? Okay. Okay. You want to let it reboot and finish our session? We still got 10 minutes if you have time. I don't know what your schedule is. It's probably going to take about 5 minutes to reboot, but okay. I will just leave. I will leave GoToMeeting on, and you can log back in under the same meeting ID number as soon as you. Sure. Nope. No problem. I'll see you when you get in there. Okay. Bye-bye. John? You have to unmute the microphone at the top left. John, can you hear me? I cannot hear you. If you're not sure if that computer has a microphone on it, go ahead and call me and we'll finish the session, the audio, by phone. Yeah, hi John. Looks like you're on a different computer. That the audio, yeah, the audio isn't working on that computer. So let's finish the audio by phone. And you're still able to see my screen fine? Okay. Okay, here. What this technique allows you to do is handle all integrals of the form, no matter what m or n are. You can use that technique to solve these. Even if they're not whole numbers, m can be to the 1/2. In other words, if I have the square root of sine of x. Even if it's in the denominator. In other words, any combination of sine, cosine, you can use this technique. Now, it gets a little bit more complicated if they're bigger numbers. In other words, if I merely do this, make that cosine to the 4th of x dx, I'm going to do exactly the same thing. I'm going to pull one sine out of there, leaving a sine squared, and then use the Pythagorean identity to put it all in cosine. In other words, make that what's left over 1 minus cosine squared.
Okay.
And then I will have, in other words, I can handle bigger numbers without problem at all. If they're both even, there are ways to handle it also. It's a little different technique, but I don't think we want to spend the time required to go over. And there's a similar technique if you have tangent secant. Okay. Turns out, I think I heard you on the other mic. Say something, John.
Hello?
Yeah, I'm going to hang the phone up.
Okay.
We don't need the phone anymore. You can hear me over the speakers?
Yeah, I can hear you.
Okay. So I can handle any combination of sine, cosine, and I can handle any combination of tangent, secant. And guess what? That covers all trig functions. Any kind of trig function you have can be put into either that format or this format.
Okay.
So this is a super valuable method of integration that is, it's definitely a part of Calc BC, but it doesn't look like they spent a whole lot of time talking to you.
No, they did not.
Okay. Well, hopefully this will get you through. Like I said, the 3 things you got to remember to do these problems are that.
Okay.
Let's go cosine next. Because that is 1 plus cosine of 2x over 2. And sine squared is 1 minus cosine of 2x over 2. So whenever you're dealing with something like that or that, just split it up into this, and we know that that's easily integratable, so is that. All right. I think we're done with this page.
Yeah.
Let's see, I think this isn't quite next. Here, let me do this. All right. You're going to get a lot of questions like this. In fact, I noticed there's 3 or 4 of them on just the materials you sent me.
Okay.
So let's make sure you understand this perfectly. You know how to do 84?
Yes.
Okay, what's the answer?
So the graph of f prime, the derivative of f, is shown above. On which of the following intervals is f decreasing? Well, f is decreasing when the slope is negative.
Okay.
And the graph of f prime is the graph of the slope, so that would be from 0 to 2 and 4 to 6.
Beautiful. That's the biggest thing they're going to test you on, is that if the function is increasing, its derivative is positive. If the function is decreasing, its derivative is negative.
Right.
About 81.
81, let f be the function with the derivative given by f prime. How many relative extrema does f have on the interval 2 to 4? Well,
again, they're giving you the derivative function, not the function.
Right.
So
would we set that equal to 0?
Yes. In other words, extrema are only going to occur when your derivative is 0.
Right.
And on the interval 2 to 4, how many of those do we have?
2 to 4, so about 0,
Are you allowed to use a calculator on this problem?
I am not sure. I don't think so.
I would think you would be.
Okay.
Only because these are hard to solve without a calculator.
Yeah, I mean, I would guess probably about, since it's from about pi over 3, or 2 pi over 3 to about a little over pi, it would probably be 2.
If that were equal to pi, would that be one of them? Sine of pi is equal to 0. Okay?
Right.
Okay, so that's one of them, and that is between 2 and 4.
Right.
Question is, are there more? The other place that sine is equal to 0 is at 0, but there's no way that can be 0 because x squared is always positive.
Right.
Another place that it's equal to 0 is at 2 pi. In other words,
it's 1.
0, pi, and 2 pi. Well, the only one I can see that's in our interval is pi. Right? Because 2 pi is 6.2. Pi is 3.14. 0 is 0. So those 3 points where the sign would be equal to 0, only one of them is in our interval. I'm going to answer that right there. Okay, and I'm pretty sure that's correct. I would be more comfortable if I could graph this and notice where it's equal to 0.
Right.
And I think you're only going to find one spot, which is at x squared plus 1 equals pi. Oh, that actually matters. No, it doesn't. No, it doesn't. In other words, it's true that x squared plus 1 has to be equal to pi, which makes, x squared equal, instead of 3.14, 2.14. And that's x squared.
Right.
X is the square root of that, which is not in our interval. So we need to go up to 2 pi. In other words, where is that equal to 2 pi? That means x squared would be equal to, instead of 6.2, 5.2. X is equal to the square root of 5.2, which is in our interval. So I still only have 1, even though I didn't show it properly the first time.
Right.
I only have 1 point in this interval where the sign of x squared plus 1 is equal to 0.
Right.
Yeah, okay. You tell me when you have to go. I'm willing to do another problem or two.
Let's do this last problem on this page, and then we'll.
Okay. Now,
So,
here's definitely one where it looks like we need to graph it.
okay.
Because we know that f is increasing. Let's see, maybe not. I think we do, though. I don't think we have a way of figuring this out without a calculator. Hold on a second. Let me just take a quick peek at this thing. So, again, they want to know where the function is increasing. So we're going to say wherever this is positive.
Right.
Not greater than or equal to 0, but greater than 0. In other words, where it's equal to 0, the function is neither increasing nor decreasing. It's flat.
Right, and that only happens once on the interval from 0 to 2. And it's from, about 1 to 1.5.
And were you figuring, are you looking at a graph of it?
Yeah.
Okay. And I'm not sure I know how to figure this out without a graph. I guess we could use the sum and difference formula. But then we're going to have lots of sines and cosines.
Right.
Which isn't going to make it any easier.
No.
So that's all I would do is graph that and look at where your graph is above the x-axis.
Yeah. So, yeah.
Between 0 and 2. Yeah.
Okay.
Good to go for this evening, John?
Yep. Thank you so much.
I'll talk to you next time.
Bye-bye.